When a crystal grows successfully, it does so by accepting and then rejecting nutrient. The rejection is crucial to eliminate mistakes. This balance is achieved through the very small, often sub-kT free energies of crystallization. The purpose of CrystalGrower is to simultaneously simulate crystal habit and surface topography, as the latter is particularly sensitive to these small free energies. The experimental data against which CrystalGrower should be matched first includes the crystal habit from microscopy or crystallography techniques. Here we can also see optical birefringence in these crystals, these lower crystals, which should also be taken into account. Then we can use atomic force microscopy to determine nanoscale surface topography. This can be done in an in situ manner, as we see here, and we can see spiral growth, we can see layer by layer growth, we can see the shapes of the terraces. And if we look at many different systems, you'll see specific signatures of the surface topography depending upon the crystal system that we are looking at. So here I want to simplify the theory which is used in CrystalGrower. So imagine that you have a growth unit. This could be in solution, so in which case there would be a solvent. And then we first of all consider the solid phase here. Then here is the growth unit completely surrounded by solvent. Here's the growth unit where some of the solvent has been removed and replaced by crystal here. And here more of the solvent has been replaced by crystal until we've replaced all the solvent by crystal, and therefore we have the bulk solid phase. Now we make the approximation in the solid phase that these all have the same entropy. So that's the solid phase. These are all coming from the solution phase. So to make the relationship between these energy levels, these free energy levels in the solid phase and the solution phase, it's useful to first of all go via a liquid phase, where we essentially go from here, we introduce the disorder in the liquid phase. So what we've done there is we've introduced the entropy change upon melting of that solid, and so the free energy difference would be T times delta S of fusion. Now that we've got the liquid phase, we can now add more solvent to make the solution phase. There'll be very small enthalpy differences, so if we ignore those and we just consider the entropy differences, then we have an entropy of mixing, which would be RT log of the solubility. That could also be an entropy of dilution. So on the solid side, the most important site is the kink site here in the middle. And the reason why that's so important is because maybe 99% of the crystal grows via kink sites, and consequently the chemical potential of the crystal is, to all intents and purposes, the free energy at the kink site. And when we're at equilibrium, the free energy of the solution phase must be equal to the free energy of the kink site. So this energy level and this energy level at equilibrium should be at the same height. Now when we start our crystallization, we start from a supersaturated solution, so we are not at the equilibrium level here, but we are at some higher energy here, whereby we add nutrient at a higher free energy. If that was a framework material like a zeolite, that could be the gel phase. And the energy, free energy above the equilibrium state will be RT times the supersaturation. So this is the energy level diagram which we're using in the CrystalGrower software. On the solid side, what becomes important is how different each of these energy levels are to the kink site. So the delta G of the surface sites, that's the S here, relative to the kink site. And there will be lots of these energy levels, these free energy differences, one for each of the energy levels. So now if we know all of these free energy differences at the surface sites in the solid phase, and if we know the supersaturation, then we can determine the probability for growth versus the probability for dissolution. This is the component for the solid phase. This is the component for the solution phase. So let's now consider in a more pictorial fashion what's happening in crystal growth. So let's suppose we start with some component in the solution or the gel phase if it was a zeolite. So we're going to be in this energy level here, supersaturated state, and we're out here. And let's suppose we try to nucleate a surface site on a crystal. That will be entering one of these higher energy levels up here, and consequently the most likely fate of this particular component here will to jump back out into the gel into the lower energy state. So anything that grows will just keep on coming back out into the gel phase. Now let's suppose we grow at an edge site here. Well, we're at a lower energy state in the solid phase, but we're still above the energy in the gel phase, so we're probably still more likely to come back out into the gel phase to try to lower the energy state there. However, if we get to the kink site, now we are lower in energy than the supersaturated state, so we're much less likely to come back out into the solution phase, and therefore the crystal is likely to grow quite successfully via the kink site. If we go into a higher coordination site as we have here, well then that is very much likely to stay in the solid state and is unlikely to come back out into the gel phase now, and so we'll become stuck within the solid. And similarly, if we go to a very highly coordinated site, very unlikely that will come back out into gel. It will stay stuck there in the solid state. The most important state, as I said before, is the kink site, and as we can see, when we add the kink site, site C, the important thing about that state is it doesn't change the formation at the crystal surface. The topography at the crystal surface for that particular site remains the same. If we have a more complicated system, let's first of all consider we had a compound with a stoichiometry AB, then the energy level diagram for CrystalGrower would look something like this. So we would have a set of energy ladders for A and a set of energy ladders for B. The kink site for the two of them will be at the same position. The spacing between the ladders may well be different to one another. Each of these will have their own solubility and their own delta S of fusion associated with them. So for site A, another one for site B. If we consider the entire compound AB rather than the individual components A and B, that would be the red energy levels over here, whereby here we have RT log of the solubility product here, which is just the summation of the individual equilibrium concentrations in their log form, and here you'd have the summation of the entropy of fusion terms. So in this particular case, if you add the red dotted line, the two red dotted lines here together, you should get the difference between this equilibrium state in solution here and this top energy level over here. If you go to a more complex system still, let's suppose you have an A2B compound. In CrystalGrower, you are not growing this as an A2B compound. You're either growing A or you're growing B. So it's growing A twice as fast as it's growing B because of the stoichiometry. So it's either growing A or B, but it's doing it in these individual energy levels. So now you have 3 energy levels, 2 of which are the same as each other. And again, if you add now these 3 individual components together, that will make up for the A2B compound the difference between the equilibrium state here and the top state here, each one of these being the sum of the individual components. So as an example of that last system, let's suppose you had a metal organic framework MOF5. It has this stoichiometry. It has a metal group Zn4O. It has an organic linker BDC with a stoichiometry of 3. So we have 3 linkers, 3 BDC linkers, each with their energy states. We have a metal component, Zn4O, with its energy ladders, and these 4 energy ladders will sum up to the total energy state from the equilibrium state right up to this top energy ladder here. Now those energy levels work well for systems such as molecular crystals or ionic crystals or metals, but when it comes to framework systems we can also use the same approach, but it becomes more convenient actually to consider framework materials such as zeolites and related materials in a different way. So zeolites, generally speaking, are made up of cages, and what I'm showing you here is the surface of a particular zeolite, zeolite A in this case, whereby it's broken down into its individual cages. Here you can see on the surface of the crystal a large alpha cage, and then we have the smaller sodalite cages and the smallest double 4-rings. Now at the surface of the crystal we have what are called Q3 sites, where you have 3 coordinated framework components. Internally in the zeolite, when they're fully condensed, they've all turned into Q4 sites. So the surface is less stable than it is internally. Now these closed cages are very important because they turn out to be the rate determining steps in a growth process. So they are not the growth units from which they grow, but once they are formed on the surface of a crystal, they are persistent in time, and therefore these units, which are the units of growth, not the growth units, are very useful in a kinetic Monte Carlo simulation as the rate determining steps. So our energy level diagram is broken down somewhat differently. Imagine, say, this large alpha cage at the surface of the crystal, or out in solution, or in the bulk solid. Well, these would all have different, these would be different free energy states, so you can start to build up an energy diagram starting from the bulk, say for the alpha cage, where this one in solution is at the top energy state, this one on the surface site is some energy level further down, and the bulk is at the bottom state where everything is in Q4. So at the top everything is Q3, the bottom everything is Q4. In this particular case there are 49 rungs on this ladder, because there are 48 vertices here which can all be Q3 or Q4. As you switch each one from Q3 to Q4, you drop down 1 rung on the ladder. Similarly for the sodalite cage, there will be different sites. This time there are 25 rungs on the ladder because there are 24 vertices in this cage. And finally for the smallest cage, the double 4-ring, there are only 9 rungs on the ladder. So these would be your solid free energy sites. Now they are not balanced around the kink site here, they are simply balanced at the point where there are no Q3 sites. So for example, we go up to this energy level. Here we've turned one Q4 into a Q3 at this point here, and here we've turned one Q4 into a Q3. But we have the ability to say, well, is the Q3 in a double 4 ring exactly the same energy as free energy as the Q3, one Q3 in a sodalite cage? Is it the same as one Q3 in an alpha cage? So this would be the energy level diagram, and then on top of that you would need the free energy in the solution phase, the driving potential, chemical potential of the solution phase. So for a zeolite, that would be your energy level system. Now the CrystalGrower software at this point is actually linked with another software called Topos Pro, which has been written by Vladislav Blatov in Samara and serves as a useful starting point for the CrystalGrower routine, because his program Topos Pro computes three-dimensional tilings, which are actually the rate determining steps in the crystal growth. So for example here, when you have the Cabazite CHA system or the Alpo 18 AEI system, you have two forms of tiling, and those tiles are the rate determining steps which can be input directly into the CrystalGrower software. Here's another one for zeolite L, and you get quite complex structures forming. Here's one for ZSM5, the MFI structure, where you have 10 different tile types. But we have an automated way now to compute these in Topos Pro and output the starting structure file, which is then input into the CrystalGrower software. So what CrystalGrower does in essence is described in this paper in Nature. We have a new Monte Carlo code that can determine the growth energetics essentially for any crystal structure. It can determine both the habit and the surface topography simultaneously. It first of all determines all the possible growth sites, so all those sites which we have on the solid side. It determines the consequences of growth on all the neighbours as the crystal grows. It does this in an efficient way which allows you to grow quite large, almost micron-sized crystals, depending on the complexity of the system. And it also gives you the ability to include defects, additives, and to some extent, at the moment, intergrowths as well. So let's just look at the whole process in action. I'm going to consider here zeolite A, which is made up of these three different cages. Here's the experimental data against which we're going to match our simulation. So first of all, we've got the habit of the crystal from scanning electron microscopy, and then 3 atomic force micrographs of the topology of 3 different facets of the crystal. So then if we grow the crystal in silico, first we start at high supersaturation, so we're getting a lot of surface nucleation. Then we're lowering down towards equilibrium, we're getting Oswald ripening, and then we get the final habit of the crystal and the surface topography of the crystal. We can do that simulation on a laptop or a supercomputer. We can just do that to a certain size, even within a few minutes, and consequently we can do thousands of different simulations if we wish to. So in this particular case, we've changed the free energy ladder spacings for the alpha cage, the double 4 ring, and the sodalite cage. These are all different simulations. If we just pick some of them out, we have different crystal habits, different surface topographies. Most of them are incorrect, so we just do many simulations, and eventually we focus in on the ones which match what we're actually seeing experimentally in order to pin down those very, very small free energies of crystallization. We also get out from the simulation not only the topology but all the surface structure, and we can even look at the terminations, the crystal termination which comes out of the program. And we can do that under different conditions of high supersaturation, we can add in this particular case, a screw dislocation running from the top of the crystal to the bottom of the crystal, and you can see as soon as we have added the screw dislocation, the crystal has lengthened along the direction of the screw dislocation, and that's because it's growing faster along that particular direction. We can come towards equilibrium, and the crystal grower can find the equilibrium point naturally. We can do that with or without a screw dislocation. And all this helps us by comparing with experiment to pin down those very, very small free energies of crystallization.